I think so. Yeah, let's get started. Okay. Hello and welcome to this snowy and cold January second Saturday presentation. Tonight we're going to be talking about commercial spaceflight. My name is Marc Polansky. I've been a volunteer here for about 6 or 7 years. I tend to lose track of time because it's so much fun. I'm a volunteer, and I'm also on the imaging team here. So if you've seen our calendars or any of the images printed out and floating around the building, I'm responsible for most of those. So tonight we're going to talk about commercial spaceflight and the excitement it has generated in recent years. We're going to cover what commercial spaceflight is and how it differs from traditional spaceflight, meaning like the Atlas and Delta rockets and what's new and exciting about them. We're going to cover suborbital flight versus orbital flight. There's a lot of misconceptions about what orbit actually is, so I wanted to cover what that actually means in terms of spaceflight. We're going to talk about a couple of the companies as well as their vehicles and capabilities of how we get to space, and we'll talk about the benefits and the importance and why it matters. So let's jump right into what defines commercial spaceflight versus regular spaceflight. Obviously it has to be spaceflight. You have to get into space. At this point, space is generally accepted to be above what's called the Kármán line, which is about 62 miles above sea level. That's the generally accepted area of where aeronautics ends and where astronautics begins. Aeronautics being how airplanes work, using flaps and wings to maneuver through the air, versus astronautics where you need thrusters and things to maneuver without having air. If you think about that distance, that 62 miles, it's basically the distance between here in New Milford and New York City, which is really not that far if you think about the size of the planet. It's just straight up, but it kind of shows you how thin our atmosphere really is relative to the size of the planet. So to be considered commercial, it basically means it's not developed or paid for or funded by a government organization. So like NASA would be an example of a government organization. We're going to talk about spacecraft that were not directly influenced by NASA, that were developed independently and privately by these companies for different purposes. Now this is different from how, say, like the United Launch Alliance or ULA operates. They launched the Atlas rockets, the Delta rockets. Those rockets originally started out as intercontinental ballistic missiles back in the 60s and 70s. And so they were funded by the Defense Department primarily, so they're considered government-sponsored or government-developed rockets, so we don't count them as commercial. Same thing with the Space Shuttle and, let's say the Saturn V. They were developed for a specific purpose by the government to further space travel, so they are not considered commercial. Generally, to be considered commercial, it also has to be available for purchase. So say a university or a company develops a satellite that they like to place into orbit, they can contract with one of these companies to launch their payload up into space. So orbit, what is orbit? There's a lot of misconceptions about getting into space. A lot of people think if you just go straight up and get into space, you'll just kind of float there. But that's not really how it works. If you go up, gravity's going to pull you right back down. Orbit's more about moving fast than moving up. In the movie Toy Story, Buzz Lightyear thought he could fly. When Woody pointed out to him that you're not really flying, you're just falling with style. And that's essentially what orbit is, except instead of style, we're talking about lots of speed. In its simplest terms, orbit is basically traveling fast enough that you are falling around the curvature of the Earth. To get to low Earth orbit, you need to be traveling about 17,500 miles an hour, which is about 5 miles every second. For perspective, that's getting from here in New Milford to New York City in about 12 seconds. So it's pretty quick. So think of it this way. If you take a baseball and you throw it up in the air, it's going to come right back down when you catch it. That's how gravity works, right? So if you take that same baseball and throw it away from you instead of straight up, it does the same thing. It goes up and comes back down, but now that you've given it horizontal velocity, it tends to travel further before it comes back down. If you throw the ball even harder or faster, it goes further, but the same idea applies. It goes up and then it comes back down. But because it has more horizontal velocity, now it's traveling further away. That make sense? So let's take that concept and throw the ball a little bit further. let's zoom out so we can see the curvature of the planet, say from New York to London. If we throw this ball really, really hard, really fast, it still goes up and it comes back down again. But now you can see that arc is starting to match the curvature of the Earth. So if we threw it just a little bit faster, you basically miss the planet. The ball goes up, but as it comes down, it's coming down past the surface of the planet. So what happens then? If we zoom out more, you can kind of see what happens. The ball goes up and it comes down, and it's falling around the planet. So there's sort of a caveat here, in that the speed has to be just right for this to work, right at that 17,500 mile an hour mark. If you're not going fast enough, the ball will go up and end up coming right back down again, just like we saw before. If you throw it too fast, it ends up going up and around and missing the planet entirely and flying off into space. It escapes Earth's gravity well if it has too much speed. And that's sometimes not a bad thing. If you wanted to get to the moon or get to anywhere else in the solar system, you would have to escape Earth's gravity well, so you'd want to have that extra speed. It's also useful for changing orbits. There's not just one orbit. This is, say, an example of low Earth orbit. There's multiple levels of orbit beyond that all have different requirements. So what are they? The most common orbit that we tend to think about is low Earth. That's that tiny little blue sliver within the center right by the planet there. That's where all the popular spacecraft tend to hang out. The International Space Station is there, the Space Shuttle flew there, and the Hubble Space Telescope is within low Earth orbit. It takes about 17,500, 450, ballpark, miles per hour to stay up there. And it's anywhere from 100 miles to 1,200 miles above the Earth's surface. Beyond that, you have medium Earth orbit, or MEO, which takes less speed. We'll get to that in a second. This is 1,200 miles up to 22,000 miles above sea level. So, a note here, low Earth orbit, it takes about 90 minutes to do a complete circle around the planet. So like the International Space Station, if it was going overhead, you'd see it roughly every 90 minutes. Of course, its orbit's more complicated than that. It tends to go all over the place. But that, on average, they see a sunrise and a sunset every 90 minutes. Medium Earth orbit takes about 12 hours to do a complete lap around the planet. And as you get further out, going to geostationary orbit, it takes 24 hours to do a complete lap around the planet, which makes sense. It's called geostationary because that's the point where the speed of your orbit matches the rotation of the Earth. So as Earth is turning, the satellites are staying in the same spot relative to the surface of the Earth, which is super useful for communication satellites like TV. Like if you have a direct TV receiver, you point your satellite up at the right area of the sky, and it just stays there. You don't have to reposition your satellite more often than not, because those satellites are stationary relative to Earth as it turns. Also useful for weather satellites, because they're taking pictures of the cloud layers and of the precipitation and any storms around the planet. Excuse me. And they're always looking at the same area of the planet, of the sky, or of the surface. So super useful. You notice that the speeds decrease the further out you go. And the reason for that is Earth's gravity. In low Earth orbit, gravity is roughly the same as it is on the surface of the Earth. So you need a tremendous amount of speed to be able to stay above that and fall around the curvature of the Earth. Medium Earth orbit, gravity starts to taper off, so you need a bit less speed, about half the speed necessary. By the time you get to geostationary, you're at 7,000 miles per hour. High Earth orbit is between geostationary out to the moon. For reference, the moon orbits at roughly 2,288 miles per hour. So you have 2,300 miles an hour versus 17,000 miles an hour, and that's because the effect of gravity drops off significantly the further away you get from the planet. So, orbital versus suborbital. We talked about orbit, so we know what that is now. Suborbital means you're not quite getting to orbit. You're getting up into space above the Kármán line, but then coming right back down again. Generally, a suborbital flight ends up around 2,500 miles per hour, which is well less than the 17,000 you need to stay up there. It takes a significantly higher amount of energy or propellant to reach orbit. It's much more difficult and generally accomplished with multiple stages of rockets. So a lot of the spacecraft companies that are getting to orbit are doing this by having a large first stage that just basically gets you up and out of the atmosphere and then when that first stage runs out of propellant, it'll break off, fall back to Earth to get that weight saved. And then that second, much lighter stage will have a second rocket engine that will light up and propel itself the rest of the way into orbit. So there's a lot more that can go wrong, a lot more moving parts, a lot more propellant. It's generally a much greater challenge to get into orbit. So let's talk about some suborbital vehicles. First we're going to touch on is Virgin Galactic and their White Knight 2 Spaceship 2 combo. This was originally developed by Scaled Composites as part of the Ansari X Prize, which was a $10 million reward for a private company to develop a spaceship that can get humans up above the Kármán line and then back down safely twice within a 2-week period. The goal here was to spur innovation into reusable spacecraft, and it did it. There were a handful of participants, but these guys won it. So they got a $10 million reward for developing this rocket, and it evolved into now White Knight 2 and Spaceship 2, which they're turning into a commercial venture for the purposes of space tourism and doing suborbital research. The basic idea is it's an aircraft. It's a custom-designed aircraft that has the spaceship suspended between the two fuselages. It flies up to about 9 miles in altitude and then drops the spacecraft. And then the spacecraft ignites a rocket engine, which then flies itself up above the Kármán line. This gets to about 68 miles in altitude, so it's about 6 miles above that level for space. And what's cool about this design is it can act as both an aircraft and a spacecraft via this feathering mechanism they have, where the rear fins or the rear wings can fold up, and it can basically mimic the way a space capsule, like one of the Apollo capsules, would come back down to Earth in terms of scrubbing off speed and slowing down before it unfolds again and then glides down to its launch point. So more of a traditional aircraft than a rocket, but it still gets into space, and it's still pretty cool. The main use, again, is space tourism, getting people up above that Kármán line so they can be considered astronauts, which is true. If you fly in one of these things, you'd technically be an astronaut. And it can also do some short-duration microgravity research. Traditionally, companies or universities that are developing experiments to fly in microgravity have a hard time calibrating them because we have gravity here on Earth. So if they're developing an experiment for the space station, they want to make sure that it works properly when it gets up there. So what they can do is, traditionally they'd use one of NASA's parabolic aircraft, which is an airplane that flies up to a certain altitude and then falls at the same rate gravity is pulling it down. So inside the aircraft you end up experiencing maybe 30 seconds of microgravity. That's how they've been calibrating their experiments, which is terrible because you only have 30 seconds at a time. So with this you'll at least get a few minutes, anywhere from 5 to 10 minutes of 0G to calibrate and do what you need to do. So there is some benefit there. Next suborbital vehicle we're going to talk about is Blue Origin's New Shepard. This is more of a traditional rocket in that it's a booster with a capsule mounted to the top of it. But what's unique about this is it's a fully reusable rocket, whereas the aircraft of White Knight 2 and Spaceship 2 are designed to take off like an airplane and land like an airplane. This takes off like a rocket, and you can't really say it lands like a rocket until now, because rockets generally didn't land. So they were the first to accomplish that. We'll talk more about that later, but it was named for Alan Shepard, who was one of the Mercury 7, who was one of the first American to reach space, to get up above that Kármán line and come back down. It gets to about 2,300 miles an hour, and it gets to about 64 miles in altitude, so just about gets up above that 62-mile limit to get into space. And the purpose is about the same as Spaceship 2. It's for space tourism and suborbital research. Basic idea here is the booster starts vertically, it launches. As it's accelerating, before it reaches the apex of its trajectory, the capsule will separate and continue on up into space, spends a few minutes up there, and then it comes back down. As the capsule comes down and deploys its parachutes, the booster reignites its engine and decelerates itself slowly back down to Earth, where it deploys some landing legs and it just kind of plunks itself down, which is pretty cool. So let's get into Orbital. Oddly enough, the first company we're going to talk about is Orbital ATK. These guys are kind of like the old guard in terms of spaceflight. They've been doing it for a number of years, but not as developing their own rockets. They've been building parts for other rockets, like engines, and they were responsible for the solid rocket boosters for the space shuttle, and soon for the Space Launch System. What's unique about them is they This particular rocket, the Pegasus, is air-launched. It doesn't start like a traditional rocket with a gantry and a platform. It gets stuck to the bottom of an airplane, flown up to about 9 or so miles, 8 miles, drop, just like White Knight 2, drops Spaceship 2, and it ignites a 3-stage rocket to get up into orbit. It's light duty. It can only carry about 1,000 pounds to low Earth orbit. The nice thing about it, though, is it's not really governed by weather because they're flying above the clouds, and it can fly out of a number of different places. So there's a lot of flexibility here, which is something you don't really see with launches. Its primary use is launching small satellites, again, under 1,000 pounds, which sounds like a lot, but in terms of spaceflight, it really isn't. Orbital ATK also has the Antares spacecraft, which has been more in the news. This was designed mainly to carry cargo to the space station. After the space shuttle retired, NASA realized they didn't really have a way to get any supplies or anything up to the space station other than relying on like the Russian Soyuz and the Japanese HTV. So they put out a contract and a call for commercial companies to step up and say, okay, yeah, we can launch some cargo for you. So Orbital took up one of the contract slots and developed this Antares rocket and Cygnus spacecraft to launch cargo up to the space station. This vehicle is fully expendable, meaning that no pieces of it are left over. The first stage launches up to get above the atmosphere and then detaches and then falls into the ocean, and that's the end of it. The second stage continues up into orbit and then eventually falls back down and burns up in the atmosphere. And then the Cygnus spacecraft itself berths with the space station, delivers its cargo, and then basically becomes a giant trash can. The International Space Station takes all the garbage and stuff they don't need anymore, shoves it in this thing, and then sends it off to burn up in the atmosphere. That is Antares. It's a 2-stage rocket. It can carry about 11,000 pounds. About 5,000 of that, or 6,000 of that, is the Cygnus spacecraft itself. So it can carry about 5,000 pounds up to the space station of usable cargo. Now we get to SpaceX. These are the guys really making the headlines because they are the first partially reusable orbital vehicle, meaning that the first stage can land. They're not the first rocket to land because New Shepard kind of beat them to the punch there, and Jeff Bezos, the CEO of Blue Origin, and Elon Musk, the CEO of SpaceX, kind of got in a little Twitter feud about it. But this is actually a bigger deal, and we'll see why in a second. It can launch about 50,000 pounds to low Earth orbit in expendable configuration, meaning it doesn't land. They developed the Dragon spacecraft to launch cargo to the International Space Station, and what's unique about that is Dragon right now is the only spacecraft that can return cargo from the space station. Every other launch vehicle or every other vehicle that visits the space station burns up in the atmosphere on the way back, but Dragon can actually land. So any experiments or anything on the space station at the moment, Dragon is the only way they can get that back down. So that's kind of important. Soon enough, either later this year, they're going to start testing, and early next year, they're going to start actually flying astronauts on Dragon 2. Which will then that'll be the first time that an American company or organization has launched astronauts to the space station since the space shuttle retired. For now, we've been relying on the Russians and the Soyuz vessel to get astronauts up to the space station. So this will bring it back to America. The Falcon 9 can launch a whole bunch of different stuff. Like Dragon's just one of the payloads it can launch. It can launch satellites to almost any orbit you can imagine. And it can launch a payload to the moon. In fact, we talked about the Ansari X Prize for getting into space. There's a Lunar X Prize now for landing a spacecraft on the surface of the moon by a private company. And one of the companies developing a lunar rover has contracted with SpaceX to have their Falcon 9 deliver their rover to the moon. So that'll be exciting. But the big deal here is the reusability, because this has a number of implications for the future. If you think about air travel and airplanes, how much more expensive would it be to fly if you got on an airplane, you flew to your destination, and then they threw the airplane away? That would be insane, right? You'd have to build a new airplane every time you flew. So that's basically how space exploration is working now, or getting into space. You launch your rocket, and the first and second stages fall back to Earth and either get burned up or fall into the ocean and are never heard from again. So SpaceX is trying to change that, and they've been quite successful within the last year and a half of doing that. they've been able to successfully land their first stage booster either at the launch site at an alternate landing pad or on a barge in the middle of the ocean, so they can recover these first stages and reuse them. They're expected to launch the first reused booster at some point later this year. But to give you an idea of how difficult this is, think about a Falcon 9 as a pencil, the size of a pencil. And if you're in New York City and you're at the base of the Empire State Building, you're looking up and you see the Empire State Building above you, what they're basically doing is taking that pencil, launching it up and over the Empire State Building, and landing it on a tissue box 23 blocks away. So it's kind of insane. The physics and the engineering behind it still kind of boggle my mind, like how it gets up that high, it's able to turn itself around and direct itself back down to such a precise location. But that's really kind of changed the game, and it's changing the launch industry, because now they're no longer throwing away these expensive first stages. Now they can reuse them, which will dramatically drop the cost of getting into space. So just as a comparison to Blue Origin's New Shepard, there's the size comparison on the left there. Remember we talked about how it takes significantly more energy to get into orbit than just to get into space. You can see the size difference there. Almost all of this is propellant. So New Shepard, Falcon 9, pretty big difference. In terms of the flight profile, New Shepard just kind of goes up, just about gets to the Kármán line, and then comes right back down again. Whereas the Falcon 9 has to go up above the Kármán line, get the second stage of the rocket up into a position where it can detach and continue onto orbit, while this giant rocket flips itself around, lights its engine again, boosts itself back, flips itself back around again, lights its engine again, slows itself down enough to start taking control with the grid fins, and then falls down towards the landing platform, ignites its engine a third time, and slows itself down to the point where it reaches velocity zero as it gets to the surface of either the barge or the landing pad. It's insane. And people told Elon Musk he was insane 5 or 6 years ago. They said there's no way that's ever going to happen yet. Here we are. They've landed 5 or 6 or maybe 7 of them by now. So they are really changing up the game, and it's really exciting. But not to be outdone, Blue Origin is also just getting started. They've been learning a lot with the New Shepard vehicle and using it as a test bed to develop the software and the control they need to reuse a first stage rocket. And they're developing a rocket called New Glenn, named after John Glenn, who was the first American astronaut to orbit the Earth. And they're developing a heavy lift rocket to carry up to 77,000 to 154,000 pounds up to low Earth orbit. It'll be a 2 or 3 stage rocket depending on where you end up going. If it's low Earth orbit, it'll be 2 stage. If it's anything beyond, it might be 3. And they're looking to launch that from Cape Canaveral starting before 2020. So SpaceX has sort of lit the fire in terms of reusable spacecraft, and now other companies are starting to catch on, which means we're no longer throwing the airplanes away. We're able to reuse these rockets and get into space for quite a lot less money. Of course, SpaceX is also developing their own heavy lift vehicle, but they're significantly closer. They're looking to start launching that this year. This will be 2 or 3 stages, same deal. They have an advantage in that the Falcon Heavy is basically 3 Falcon 9s just strapped together. So the technology is already there. They already have the boosters. They already function. They just have to strap them together and launch them. And all 3 of those are reusable. So when those 3 stages go up, those 3 cores, they will all return back to either a launch site or a barge. So all 3 of those will become reusable. And they're looking to, again, launch that later this year. The other kind of newcomer on the scene, and they're sort of addressing a different problem, is Rocket Labs. They're a company that's starting up a spaceport out of New Zealand. And the reason that's important is at the moment, the launch scene is kind of getting crowded up here in America at all of our spaceports. The Kennedy Space Center or the Cape Canaveral Spaceport is the most popular place to launch from right now. But it does get crowded. There's a lot of range limitations around when you can launch and when you can't launch, depending on what else is happening at the time. So it could take weeks or months to get a launch window out of Cape Canaveral. Whereas in New Zealand, Rocket Labs has signed a contract with the New Zealand government to launch a rocket as frequently as every 36 hours. So every day and a half they could be launching something up, whereas at any spaceport here we have to wait potentially a week or more to get up there. So they're developing their own little tiny rocket that's meant to push microsatellites or cube satellites up for fairly cheap. only 330 pounds. But their big news is they're opening up the spaceport, and they want to invite other companies to come and launch from there. So we could see SpaceX or Orbital or anybody else launching from this New Zealand spaceport as frequently as possible. So that's kind of where we're going. So why is it important? Why does it matter? Here's a couple of the costs of the current lineup of launch vehicles. The Atlas V has kind of been ULA's workhorse in terms of what Falcon and Antares are going after. And you can see there's already a significant price difference there. The space shuttle cost $450 million every time it launched to get 50,000 pounds up to low Earth orbit. The Delta IV Heavy has kind of taken on a lot of that work since the space shuttle retired in terms of larger satellites, but it's still a huge amount of money. So the number that kind of jumps out is the Falcon Heavy at $90 million for almost double the capacity of the Delta IV Heavy. So once that starts flying, that's going to really, really shake up the launch industry. And on top of that, once they start reusing the rockets, if they can get the cores down reliably, refurbish them, and get them flying again, their numbers could drop as much as 30% when they start reusing the cores. So they're basically going to break the space launch industry if everything goes to plan, which is really exciting because it means that we can do a lot more up in space. So again, why does it matter? Competition tends to drive innovation. For a while, launch services were pretty much stagnant, and they cost an exorbitant amount of money because the ULA pretty much knew they were the only game in town. If you wanted to get a rocket into space, they had to go up in a Delta or an Atlas or one of their bigger rockets, and they charged a premium, especially for science missions. So now that we have Orbital and SpaceX developing competitive vehicles, there's incentive to push the envelope and improve and innovate to bring costs down even more, as well as improve performance and to launch quicker. One of those innovations is 3D printing. SpaceX is one of the first companies to 3D print entire rocket parts, including an entire engine. The engine on the Dragon 2 spacecraft is a titanium engine that was developed and 3D modeled and 3D printed. And it was developed such that it would be impossible to manufacture it with traditional techniques. You couldn't take a block of titanium, stick it on a 5-axis CNC machine, and spit out one of these parts because it's too complicated or the tools just can't get there. So the ability to 3D print is really changing up how engineers are thinking about design and what's possible. As costs go down, there's obvious benefits there. Space becomes more accessible. Companies can launch satellites for less money than ever. And in terms of science, less money spent on launch means you either save that money or that money can be put towards the payload or towards the science, which is always a good thing. And of course, we live in a digital world where satellites are playing more of a critical role in everyday life than ever before. Between GPS for navigation, TV, internet, that's all going through satellites now. Weather monitoring, and of course astronomy with the James Webb Space Telescope, or the Discover satellite that got launched up by Falcon 9 last year. Beyond that, there's companies that are innovating within space itself rather than the launch market. Bigelow Aerospace is one example, where they are developing inexpensive inflatable space stations. Right now on the space station, the International Space Station, they have one of their test modules called BEAM, or the Bigelow Expandable Activity Module, where they're kind of proving the concept of these inflatable balloons that can serve as human habitat. And they have plans in the near future to launch up their own space station consisting of larger versions of these modules that attach together and effectively become a big inflatable space station. And one of their modules is, believe it or not, a space hotel. So they're getting ready for space tourism. And with launch companies driving down costs, it's not going to be that far away. So, conclusions. We're basically in a modern space race right now, which is a good thing, where rather than competing government entities, we have competing companies competing for an ever-expanding launch market. The launch technology is rapidly evolving, and with the prospect of reusable spacecraft, we're entering a whole new world. It's a really exciting time. It's especially exciting for anybody interested in space because becoming an astronaut is coming closer and closer to reality for the average person. Right now, you can reserve a spot on a Spaceship Two flight for about $250,000, which is still a fair amount of money, but think about when air travel first took off, how much it cost to get a plane ticket. So within 20, 30, or 50 years, we could be having regular space flight just as easily as we take flights, from city to city right now. More importantly, these companies are now using this technology to provide this new access to space. Traditionally, governments have had to bankroll spaceflight because there was no return on investment or business case for launching into space. It didn't make any business sense. So now that there's a market for research and communication satellites, and the technology is there to support it, this allows government entities to focus more on exploration and science than simply getting there. Because it didn't make much sense if you had, 500 million for a mission to get it into space, and 250 of it was just getting to space in the beginning. It leaves only 250 million to build your spacecraft. So the less cost it takes to get up there, the more you can put into the spacecraft itself and do quite a bit more. And living and working in space is not going to be that far off. The International Space Station has had a continuous human presence for over 16 years now. And they can host up to 12 or 13 people at a time now. And once Bigelow gets up there with their station, that's going to increase even more. And SpaceX has always been focused on Mars. And it's not going to be that long before they start landing spacecraft and even people on Mars. My prediction is within 10 years they'll get there. Launching the Falcon Heavy is the first step. Once they get there, they're going to send a proof of concept vehicle. They're going to send one of the Dragon spacecraft specifically designed for Mars. They call it the Red Dragon, out to Mars to land some equipment and some supplies as a precursor to sending humans there. So that's all happening within the next 2 or 3 years. So it's a very exciting time. So commercial spaceflight has made tremendous leaps over the last decade or two, and the best is still yet to come. So thank you for coming again on such a snowy and cold night. If you have any questions, I'll try to answer them. Otherwise, join us next month when Dr. Parker Moreland presents on the discovery of gravitational waves.